Hello everyone. Today we're going to talk about solving projectile motion problems where our projectile is shot not horizontally but at an angle. So we're going to talk about angled projectiles. And our first example is specifically when our object starts and stops at the same height. So we're going to say our delta y is 0. So it goes up, comes back down to where it started at. First example, an object gets launched at a speed of 30 meters per second. And we'll say it gets launched at an angle of 15 degrees above horizontal. We know that it's going to go on a parabolic path, landing on the ground somewhere down the road. I want to know several things. First thing I want to know is what is the maximum height that the object reaches in its trajectory. So let's list the things that we know. Actually, before we list the things that we know, if you remember back to our last unit, anytime you have a vector that's at an angle, it's always a good idea to break that vector into its components. So our x component of the velocity initial and the y component. So our x component, if you did 30 times cosine of 15, would be 29 meters per second. And our y component, if you did 30 times sine of 15, you get 7.8 meters per second. Now, going on to our max height problem here, the variables that we know our initial velocity in the y direction is 7.8 meters per second. We know at the maximum height, the final velocity in the y direction is going to be 0 meters per second. We know our acceleration in the y direction is going to be negative 9.8 meters per second squared. And maximum height means we're solving for delta y. I know this is in the section for delta y equals 0, but overall this projectile is going to land back where it started. I know halfway through it's not going to be where it started, but just bear with me for this first problem. If you look back at your kinematic equations, the one that's appropriate for this case, Vf in the y direction squared equals Vi in the y direction squared plus 2 times a times y. 0 equals 7.8 squared plus 2 times negative 9.8 times delta y. Solve for delta y, that's your maximum height, 3.1 meters above where it started. All right, same situation. Let's move on to a different question. What if I wanted to know the flight time? What do I mean by flight time? I mean how long it's in the air if it lands at the same height that it started at. So again, let's list the things that you would know for this problem. You would know the acceleration is still negative 9.8 meters per second squared. You know your Vi in the y direction, 7.8 meters per second. Your delta y, since you're going to start and stop on the ground, is 0. We want t. Look back at your kinematic equations. You've got delta y equals VIY times t plus 1/2 AT squared. So 0 equals 7.8 t plus 1/2 negative 9.8 t squared. At this point, if you're getting a cold sweat because you think you have to do the quadratic equation, fear not. You're not going to need to on this problem. If you just move one of the terms to the other side, you end up with 4.9 t squared equals 7.8 t. divide both sides by t, then divide both sides by 4.9. You get a time of 1.59 seconds. Next question for the same scenario, I want to know what is the range of this projectile. Remember, range is just a fancy term for displacement in the x direction, so I take the velocity in the x direction times time. So for this problem, our x velocity we solved for way back at the beginning is 29 meters per second. And we just had the time, 1.59 seconds. Multiply those, you get 46.11 meters. Now, in case you're curious about testing this and seeing, did I get the problem right, there are various online projectile motion simulations you can do to see if you get it right. So I'll just pull up one of them here. I'll post a link to this site along with this video, so in case you want to check your problems as you go. So let's input our data. We know that our initial height is 0 meters. We know our initial speed, 30 meters per second. Our initial angle is 15 degrees. And if we fire this projectile, boom. We've got a landing position of 45.9 meters, very close to 46, which is what we had. The reason that you get a little bit shorter range on this particular simulation is because it's setting gravitational acceleration to be 9.81. So if we reset this and change it to just 9.80, we can see if that makes a difference. Let's see, start. Gives you about the same answer. You can also see here in the middle of the screen, it tells you the maximum height, 3.08 meters. Again, that's very close to the 3.1 that we got, just within the margin of rounding. Next, I want to ask one more question for the same problem. I'd like to know at what other launch angle would you get the same range? At what other launch angle would you have the same range? This one's an interesting question. So we had a range of 46.11 meters at an angle of 15 degrees above the horizontal. The interesting thing, you might be able to kind of figure this out on your own. If you go to the complementary angle to 15, you would actually get the exact same range. Now, they're definitely not going to be in the air for the same amount of time. 75 degrees is much more vertical, much more up and down. So the projectile is going to go much higher, be in the air for a much longer period of time, but their overall range would be the same. I'll also say this, this only applies to projectiles that start and stop at the same height. If your projectile lands at a different height, don't use this, this logic. So we can test this again. We can pull up the simulation. We can see what kind of range we get when we change our initial angle here from 15. Reset. Change it to 75. Start. Notice it's in the air a lot longer, it goes a lot higher, but our overall range, horizontal position here, our maximum distance, 45.9 meters, is the same. One last question on this example. I want to know what its speed is when it lands. What is the speed of the object when it lands? So when it lands, it's going to be coming in at an angle. So we're going to break that into a triangle. You've got your final velocity in the y direction. You've got your velocity in the x direction that never changes. I want to know the hypotenuse. Okay, that's the speed that it's traveling when it lands. So we need to use kinematics to solve for VF in the y direction. Now, if we know that our initial velocity in the y direction, way back at the beginning, was 7.8 at the ground level, then we also know, since this is a perfect parabola, that our final y velocity will also be 7.8 meters per second. It'll just be in the downward direction. We also know our x velocity, going back to our original triangle, is 29 meters per second. So we can use the Pythagorean theorem to solve for v. You get 30 meters per second. Should be kind of good to see that same 30 come up again, because we start and stop at the same height. We're going to start and stop at the same velocity, or speed, I should say. We didn't throw a direction in here. If we did solve for a direction, I guess I'd imagine you could guess what the angle that this object would make with the ground if we solve for this angle in here, theta. We could say that tangent of theta equals 7.8 over 29. And so that makes theta 15 degrees.